Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. Imagine a solid object, a seemingly inert crystal, producing light not by heating or chemical reaction, but by sound. It's not a scene from science fiction, but a highly specific, complex physical phenomenon known as sonoluminescent resonance where certain crystalline structures effectively sing with bursts of invisible ultraviolet light. To understand this crystal song, we first have to tackle the general principle, sonoluminescence. Most people know this as the bizarre effect of using intense sound waves, often around 20,000 to 40,000 Hz, to create tiny, transient vacuum bubbles in a liquid, usually water. As these bubbles form and then violently collapse, they compress the gas inside so incredibly fast that the temperature briefly spikes to tens of thousands of degrees Celsius, resulting in a flash of visible light. But the phenomenon changes dramatically when a structured solid, a crystal, is introduced, or when the crystal itself is the medium undergoing internal stress. This is where the concept shifts from mere bubble dynamics to the structural physics of the crystal lattice itself. Leveraging what is often called crystalloluminescence or, in cases of mechanical stress, triboluminescence but critically, triggered by resonant acoustic energy. Certain crystals, such as specific configurations of quartz or even specially doped salts, possess a crucial property, piezoelectricity. This means that applying mechanical stress generates an electrical charge. Conversely, applying an electrical field can cause mechanical strain. When we blast these materials with high-frequency sound waves, we are, in effect, rapidly oscillating the crystal structure. If the frequency of the sound precisely matches the material's natural resonant frequency, the frequency at which its internal lattice structure vibrates most efficiently, the internal mechanical stress is amplified to extraordinary levels. This is the heart of the resonance. Instead of collapsing bubbles in a liquid, the energy is focused within microscopic structural defects, voids, or boundaries inside the crystal or at its surface interface with a fluid. The rapid, violent structural oscillation creates localized shock waves. These shock waves focus the acoustic energy into points so small that the energy density becomes immense. Think of it as a nanoscale hammer slamming into the crystalline structure thousands of times per second. Now, why is the resulting light invisible? The energy released during this focused structural collapse is significantly higher than that produced by a typical chemical reaction or even standard triboluminescence. When the internal molecular bonds break or when electrons are stripped from atoms and then rapidly return to a lower energy state, the sheer violence of the collapse dictates the wavelength of the emitted photon. Instead of generating visible light photons, the energy levels are so high they jump directly into the ultraviolet, UV, or deep violet spectrum, sometimes bordering on soft X-rays, making the singing invisible to the naked eye. This invisible UV song holds profound scientific promise. Researchers aren't just looking for novelty, they are studying this mechanism as a potential pathway for ultrafast, high-energy chemistry. The conditions created at the focal point of the sonoluminescent resonance, extreme localized pressure, ultra-high temperatures, and intense UV photon emission, are virtually impossible to replicate through conventional means. Scientists believe this controlled release of focused acoustic energy could be used to break incredibly stable molecular bonds or even initiate fusion reactions under laboratory conditions, though that remains highly theoretical. In essence, the crystal is acting as an ultra-efficient energy transducer. The acoustic wave enters as mechanical energy, is amplified by resonance, and is focused by the atomic structure, ultimately being converted into light energy. A silent, intense flash of invisible UV radiation. It is a stunning demonstration of how structure, rhythm, and energy coalesce at the quantum level to create a secret light show hidden just beyond the visible spectrum. For more incredible facts like this, don't forget to subscribe and turn on notifications.